All right, well, welcome everyone to Rethinking Building Carbon Accounting. This course is brought to you by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the places we live. And today I will be your moderator. My name is Brett Little, and I am the program manager here. As always, these courses are approved for multiple continuing education units in many different things. A couple different extra logos there I forgot to take out, but this one is just approved there for the Certified Green Home Institute program materials pedal up at the top there for what we're talking about. And AIA, Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. And one thing we always like to do is show off some exciting news from our members. So one of our members here, Mandalay Homes in Arizona, one of our lead project team actually won the US DOE Zero Energy Ready Home 2021 Housing Innovation Award. So very cool news for them, go them. They had on this particular home, they had a HERS index of 34 with an average utility cost of $80 per month, saving $1,400 a year from the code baseline. So this is what our members are doing. They're doing great things. You can see Green Home Institute, become a member, sign up, get instant access to our webinars and all sorts of other benefits. And before we get going, quick thanks to some of our top tier sponsors. We know repairing our existing homes is one of the quickest ways to reduce embodied energy. And especially when it comes to windows, we know that, a lot of times new windows are added in, but does that need to happen? So a lot of ways there are new things out there that can improve the performance of the existing windows, like window inserts. So think of storm windows kind of on the inside. You can feel warmer in the winter, cooler in the summer, and save about 20% in energy bills. And further studies have showed there's about a 10% average air leak reduction when you put in these storm interiors from Indo. These are very do-it-yourself friendly as well. You can measure to order, size, and then install. And in many cases, they can be compliant with historic commissions, which tend to be troublesome sometimes when it comes to brand new windows. So save money, reduce energy, reduce embodied energy by selecting Indo window. And then also thanks to our second tier sponsor, Rockwool. Again, another great way to reduce embodied energy for fully insulating a home from top to bottom using mineral wool compared to foam as one example. Again, these can insulate all the way around a home, exterior rigid insulation, some of the best you can do. This is a mineral-based insulation, and they are also doing some exciting things like a continuous giveaway of product, the sweepstakes, if you sign up over at ourclass.rockwool.com. And you can sign up for builder training series that they're doing and training on how to install this. So embodied energy, we talk a lot about getting to net zero energy, which is really important. But now we need to start thinking about the materials, where they're coming from going into because that's going to become most of, as time marches on, as we get more efficient in our builds, that's going to be where most of our energy is going to be coming from, or our carbon in this case. And the Green Star program, as you know, has a new item built in for new construction homes, where we want to have you evaluate and assess your carbon and then reduce it in higher levels of certification. So that's something to check out and why we want to keep having these conversations. So I'll stop here and hand it over to Scott Farbman, and he can take it away and tell you a little bit more about some of the things that he has on his mind as far as rethinking our carbon accounting. So Scott, welcome, and it's all yours.
All right, thanks, Brett. I think if you relinquish your share, I can take over and share my screen. Let me give it a shot here. All right. So hopefully everyone can see my presentation now. Thanks for the introduction, Brett. I'll give a quick background on me and my company. Don't want to take too much time talking about us, but Scott Farbman, I am a registered licensed architect, CPHC, which is a certified passive house consultant, and also I've got my LEED accreditation. started out in the architecture world, trained architect, obviously. But about 6 years ago, I pivoted over to the engineering world instead, and have been working, more so as a consultant these past couple years. And I've had the opportunity to approach things from a different side of the coin. And it's been quite interesting for me. So I'm with dbHMS, and I'm currently the innovation lead. So a good chunk of my time goes to project management, some high performance projects, and then the rest of my time goes more towards research, development, marketing, business, et cetera. And it's been a very fun process for me. dbHMS, traditionally an MEP design firm. I'm going to launch my laser pointer here. So we do all the things that a normal MEP firm would do, but then we do a couple other things on top of that, which I think makes us more, not only more interesting, but more effective in practice. So we've got a very elaborate commissioning studio, which started as systems MEP, but now offers building enclosures. So we do blower door and other tests on the commercial side. We also have a HERS radar and do some of the other single family home related items as well. And then the group that I'm part of, Database Plus, used to be our high performance studio, but we rebranded ourselves about 2 or 3 years ago. And we offer a lot of the high performance analyses that would happen very, very early in the design phase. We would be responsible for conceptual design. So if we get a project that has a net zero energy goal, it would start in our studio. We would do all the early analyses, come up with the systems concepts for that. So is it a VRF system? Is it a geothermal radiant system? What does that look like and what are the impacts there? And then we'd see it through in regards of the sustainability consulting. So we do some stuff that Brett and his company does, but we provide, everything from lead to passive house consulting now, which is something that I head up for our company. We are all over the country, but we're headquartered in Chicago. The bulk of our company is in Chicago. Our sustainability, our commissioning group is headquartered out of Michigan. And there's, I think, 10 to 15 people there heading up our commissioning. And then, as you can see, we have projects all over the US, even up in Alaska, predominantly, again, in the Midwest, but East Coast as well, as we have some Philadelphia and Boston presence. And then more so down in the South as we launched a satellite studio in San Antonio. So we're working all over the place, but at the heart of it, really focused in the Midwest. It's going to be talking about a number of things today, as Brett mentioned. What does carbon emissions mean at a global level, and what does it mean at the building level? And then I'm going to get into some of these fun analyses that we've been doing internally at our company and look at the impact refrigerant has on the total life cycle carbon emissions of our projects, and also the impact that window systems have on the total life cycle carbon emissions of our buildings. I'm not familiar with the Indo product, but it was good to see that. And I think that there's a pretty unique place for that in the marketplace. So I'm curious to dig into those details a bit more. And then I'll end with key takeaways from our studies and open it up to some Q&A. So this graph might look familiar to some of you out there. It was produced by Carbon Leadership Forum, who is at the forefront of embodied carbon, not policy specifically, but getting embodied carbon out to the public in a digestible way. This graph does come from the IPCC data. This number, most of you all are probably familiar with, 18% associated to the energy our buildings use on a daily basis to heat, cool, power equipment, et cetera. Pretty easy to get that number. We just look at our utility bills, right? Where things get a little dicey is, what about the building materials that go into the buildings that we build? There's going to be a slice that comes from industry as we get iron, steel, cement, concrete, et cetera, glass, you name it, is all coming from a slice of this industry pie. And then there's a slice of transport pie as well that funnels into industry and then funnels back into the building. So a lot of connectivity here and interdependencies as well, which makes getting that total number complicated. But the number that sticks right now in the industry is about 40%. 40% of the total global emissions is related to one way, shape, or form to the buildings we design, occupy, and inhabit. So where do those numbers come from? I'm going to kind of take you from early stages to end stages of a building here. So it starts with material extraction. Where is the raw sourcing of materials coming from that go into the buildings that we're building today to manufacture concrete, insulated panels, rock wool, anything that we use in the building starts somewhere. It's extracted or recycled, transported to the manufacturing plant where it's being produced. And then it has to go to the building site where it's being constructed. So there's, carbon and greenhouse gas emissions associated with each of these phases, and then the in-between phases as well. There's greenhouse gas emissions and energy impacts related to constructing the building. So construction energy as it pertains to cranes, even the trailers that the builders and the GCs use on site. There's energy consumption related to that as well. And then once the building's built, we have what we would more commonly refer to as the use or operational stage, which what I initially thought of is just my utility bills, energy, water, waste, et cetera. But there's other things to consider here as well, and I'll go into it in a bit more detail in a couple slides. But what happens if your drywall gets damaged and you need to replace it? There's a replace phase of this that doesn't commonly get discussed. There's embodied carbon and energy related to replacing things in your home or in the building. Another big one is HVAC systems. They probably have a life of 20-ish years. So if your building is designed to last 60 years, you're replacing that MEP 2 times during that. And where does that embodied carbon fall? Is it upfront carbon? Is it use operational carbon? It's hard to determine sometimes. Looks like we might have a question here, so I'm going to pause for a second.
Yeah, just a clarification to spell out MEP and what that is.
Yep. MEP would be mechanical, electrical, and plumbing systems. So, our furnace would be a mechanical system. Our domestic hot water would be a plumbing system, and electrical could be, the panel that provides service to our building. And HVAC is heating, ventilation, air conditioning. So another acronym for talking about providing space heating, space cooling, and fresh air to our spaces. Good question. Sometimes I got my head buried in the sand talking about this stuff, and I don't remember to define some of the basics. So at end of life too, this is a consideration. So what happens when the building is done? We see buildings demoed every day. Does that material go to a landfill? Does that material go to a recycling plant? Or does that material get kind of broken up on site and reused immediately? There's different impacts that can happen along the way, and we want to make sure that we consider them equally. So why are we talking about carbon emissions and greenhouse gas emissions now? Coming out of the Paris Agreement and the most COP26, we're talking about trying to limit global warming potential to 1.5 Celsius. And in order to do that, we have to look at a couple different scenarios here and what that means for global warming over the years. So if we were to continue as business as usual, designing buildings the way we typically design today, and in powering those buildings with the energy sources, energy mix sources that we have today, we're going to continue this rise of temperature as projected here by IPCC. So if we don't want to do that, what are our other options? We can look at peaking emissions growth in 2080, which results in this scenario. We could look at cutting that by 40 or 50 years, shaving that peak down, or we can look at a scenario in which we start to consider things on zero carbon. So similar to zero energy, but carbon too, because we need to account for anything that isn't typical energy use. And really the only way to limit the warming potential here that we're trying to reference as a threshold would be to start considering and designing zero carbon buildings. And there's no easy way to do this. It's a quite complicated process, as I was just showing on the previous screen. There's a lot of interconnections, interdependencies. It takes a lot of analysis. It's not just as easy as it is. There's no silver bullet, really. I mean, we all have to come together collaboratively to address this together. So I want to kind of explain as simply as I can the relationships between embodied carbon and operational carbon. Brett talked about embodied carbon a bit in the introduction. So if we were to build a building in 2020 and it's completed, that embodied carbon is a static number that's just out there for the rest of the building's life. And let's say we're going to look at a 60-year cycle from 2020 to 2080. So this chunk of carbon represents the extraction of materials, getting it to the plant to the site, and building it. And bam, you got a building. And this is its representation of embodied carbon. Once the building's built and it begins to become operated, we got a couple paths to look at. So a business as usual operational performance path. Let's say this is like the code minimum. Every year, the building is going to use energy to operate. And we're just going to assume it's the same amount each year. And it stacks up every year over time. And it creates a linear graph. So this is, across 60 years, how much operational energy we need to account for from the building. And we typically can derive this from an energy model that estimates that amount of energy and then turns it into carbon emissions based on where the building's located and what the electricity grid or the source energy grid looks like. So we end up with maybe a 3-to-2 ratio here, where operational energy is kind of 3 times and embodied is 2 times. This could be, there's ranges here, it really depends. But let's take a look at what a high performance building would do. So it's going to follow a similar trend, but just reduce in value or quantity here. So this is our first step to reducing operational carbon emissions, is to design a high performing building, something that has better insulation. It's got a more efficient HVAC system. It's delivering heating and cooling at a higher efficiency rate than maybe a traditional system might do. Now let's look at a scenario in which the only thing that changes is the power from the grid. So this is that same high performance building, but with a renewable energy grid. So let's say wherever you're located, whoever you're getting electricity from your utility provider has evolved to offer renewable energy. So let's say that utility provider is promising to deliver 100% renewable energy in 2050. So you're still going to have some carbon emissions associated with your building operation until they hit 100% renewable. And then from there, it's just a flat line. It's a plateau because you're no longer emitting every year, but this carbon is already out there. And in this scenario, embodied carbon really becomes a much larger slice of the pie, and something we need to consider and reduce, because it becomes more of a 2-to-1 ratio now. And we need to take a look at this and see what we could do early days in the design to reduce this embodied carbon amount. And that's what I'm going to be getting into now. So how do we assess this? We use something called a whole building life cycle assessment, or whole building LCA. This is a quite the complicated analysis. It's got many stages and steps to consider. We've got the product stage here, which has to do with, from the manufacturer. We've got the construction stage here, which includes transport to site and construction energy. We've got the use stage here, which includes a lot of the things I mentioned before, like maintenance, repair, replacement, et cetera. And then tucked in underneath is operational. So how much energy are we using each year, and how much water are we using each year? And then from here, we've got end of life stage, which includes deconstruction, transport, waste processing and disposal. So a lot of moving parts and pieces here, and a lot of things to consider. And because of this, it becomes quite a complicated process and difficult thing to achieve and execute. So EN 15, here, I'm sorry, I missed my cursor. EN 15978 is a European standard, but it's been widely adopted pretty much everywhere. And this standard is represented here on the screen. There's also this circular economy piece about reuse, recovery, and recycling. So this would include, maybe you have a CLT structure, which is a cross-laminated timber. And you can design that structure to be deconstructed and reused in a different building. So that wouldn't come up in this end of life stage as well as it would come up in this beyond the building life cycle stage. So this stage isn't required under EN, or I'm sorry, this stage isn't typically included because it's hard to plan and address, but it is something that can be planned for if designed appropriately. So how do we do LCA? We do it pretty similarly to energy modeling. So if you're familiar with energy modeling, we follow the same path. In early design, we have an analysis of the building at a high level. Maybe it's a shoebox. So it's, single plane. It's a kind of a general mass that represents what the building might look like. And we assign parameters to that mass. We say we've got a wall that's this thick with that much insulation, and we've got a furnace that's 98% efficient, really high level inputs. And we run the analysis to see what that is. And we benchmark it against maybe a code level performance building, or maybe some of the high performers in the region. We could look at Energy Star Portfolio Manager for that information, or we could look at PNNL, which is the Pacific Northwest National Laboratory that produces average energy performance and carbon performance numbers for buildings in the US. So very similar to energy performance, we're doing the same thing with carbon. So we do general quantity takeoffs of the building based on its geometry, how much wall area we have, how much roof area we have, et cetera. And we try to benchmark it against other standards. Then in the design development stage, we start to compare options. So how do we optimize things? If we have a wall assembly, do we have insulation type X or do we have insulation type Y? And how do they compare against each other? And we could start to use that information to inform our design decisions to select higher performing products, higher performing materials, or just try and reduce the quantity of that. The easiest way to reduce your embodied carbon is to reduce the quantity of materials or weight of materials in the first place. So can we optimize the design of our system somehow to just reduce that amount? Can the geometry reduce in surface area, because less surface area means less insulation? So these are the things we start to think about in the design phase. And then going into construction documentation, this is where we start to fine tune the analysis. It's more of a compliance documentation. This is where we finalize the results and say that this is predictively what we think the building is going to look like from a carbon performance perspective. So I want to start to get into embodied carbon now, because we talked about how important embodied carbon can be, especially as the grid starts to clean up and become more renewable. There's more stress on the material selection and the material design in our buildings. So this is, I'm going to call a typical breakdown of where embodied carbon goes in our buildings. And it typically goes to what weighs the most, because if it weighs a lot, it's got a lot of volume, density, et cetera, it's going to have a lot of impact. So structure is typically that biggest piece of the pie. I've got it here for like maybe 40%, but it could be upwards of 60% when you include foundation, beams, columns, roof structure. All that really adds up quickly. From there, the second biggest impactor is typically envelope. Like I said, if you have a lot of surface area, you have a lot of envelope. And if you have a lot of envelope, you probably have a lot of insulation, or you probably have a lot of windows. And all those things add up to have a considerable impact on your total carbon emissions of the project as it pertains to embodied. From there, We have two other big slices. We've got MEP systems, so mechanical, electrical, and plumbing systems, which include the equipment themselves, and then also the distribution of that source. So pipes for your plumbing, ductwork for your HVAC, that all gets accounted for. And then a big one that we're seeing more recently is the impact of refrigerant, and I'm going to get into that in a little bit here. Finally, we have finishes, so your flooring product, your drywall, et cetera. Usually the last big system impactor of the equation, and a couple small slices here like appliances, other equipment, and site improvements or site infrastructure. So first, I'm going to talk about MEP. Like I had said, it could range from 10 to 20% of the total embodied carbon of the project. And this is why the number could be so high. So in our HVAC systems, let's call it a heat pump. Heat pumps use refrigerant to transfer heat from one place to another. And that refrigerant can have a considerable impact on the greenhouse gas emissions of the project. The main reason why is because the most commonly used refrigerant right now is R410A. And R410A has a global warming potential of 2088. So it's 2088 times more harmful than carbon dioxide, which is down here at a value of 1. So you could see if we have buildings that use refrigerant with something that is 2,000 times more harmful than carbon dioxide, how that MEP slice could start to grow comparatively to the rest of the building. So there are technologies out there that use carbon dioxide as a refrigerant, and it would have a global warming potential of 1 because it's the same as carbon dioxide. And I'm going to talk about those in a little bit here. So this is really to set the stage as to why mechanical systems could have such a big impact on your embodied carbon. So we did a study here at dbHMS because we design mechanical systems all the time. And we took one of our buildings that is a 6-story multifamily building in Chicago. It's about 100,000 square feet. And we wanted to test 4 commonly used mechanical systems: a packaged terminal air conditioner, a PTAC, or like it's called a magic pack sometimes. It's in wall. I'll show it on the next screen. We looked at a variable refrigerant flow system, or a VRF, which is something that we're designing quite frequently now. And I'll define that again on the next screen. We also looked at a water source heat pump and a 4-pipe fan coil unit. So what's the differences between these 4 systems? It's really the boundary of refrigerant. And I've got that highlighted here in orange, if you could see it. So the boundary of refrigerant changes on these 4 different system approaches. A 4-pipe fan coil unit has a chiller that has a packaged chiller with refrigerant in that chiller. From there, it's supplying hot or cold water throughout the building to do space conditioning. So refrigerant really isolated to this one singular piece of equipment. Same approach in PTAC. The refrigerant is isolated into this through wall window unit where we're doing heat exchange from inside to out. So again, isolated to packaged. That's something to think about. Same difference here with water source heat pump, but kind of a meld between these two. So a water source heat pump, there's a central plant that distributes condensing water throughout the building. And then there's an exchange of heat between that condensing loop and the indoor unit, the water source heat pump, which has refrigerant in it. So kind of this hybrid approach, right? And then there's VRF. VRF has outdoor units and it has indoor units, and refrigerant is pumped between the two. And this is a pretty common approach now because it's become cost effective. And in terms of energy use on an operational side, it's very energy efficient. But as a result, VRF ends up with the most refrigerant in your building at, on average, 815 pounds in this study we looked at. So these other packaged units, PTAC, remember, was that through wall packaged unit, had about 500 pounds. That water source heat pump, again, that packaged unit has about 600 pounds. And that fan coil unit with the chiller, the centralized chiller, has about 500 pounds. So in terms of total refrigerant between these three options, very similar. VRF, though, because you're pumping refrigerant through the building from outdoor to indoor, has more refrigerant just by sheer weight. As a result of the VRF pumping refrigerant throughout the building, all of those pipes are field installed and have, field installed connections, fittings, et cetera. And due to that installation process, there's a higher possibility of refrigerant leakage annually. You could see on the high end, we're looking at 9% annual leakage versus about 4% on the packaged unit. So if it's packaged in the manufacturing plant, there's a way less likelihood of there being any leakage involved with that piece of equipment. Same goes for end of life. So if you're removing that piece of equipment from the building, there's going to be some leakage inevitably as you dispose that piece of equipment. In the VRF, it's almost 2 times more, it's about 20%, so quarter more than these package units, because again, you have all that field installed refrigerant that's running through the building and you need to get it out of the building and decommissioned. So what does this look like when we look at it in the big picture? And I'll try and set the stage here. So this is the total carbon emissions of this hypothetical 6-story building, about 100,000 square feet, right? Across a 60-year cycle. And we've got carbon associated to annual operations here in green. We've got carbon associated to refrigerant impact, which includes upfront refrigerant, as well as leakage and replacement each year for 60 years. And then we have embodied carbon with the rest of the building, so the structure, the enclosure, et cetera. And what we see typically on a building like this is operational is still heavily dominating the the total life carbon emissions of the building. And if you remember on the previous slide where VRF has a higher probability of leakage and a higher amount of carbon, a higher amount of refrigerant by weight, it's got the highest amount of refrigerant impact here. But what's interesting to consider is it is the most operationally efficient. So you're making some trade-offs here. You might have a higher impact on embodied carbon through refrigerant, but you've got a smaller impact each year because you're using less energy because the system's more energy efficient. So that's something to consider and something we take a look at in depth when we're designing these systems. The lowest amount of refrigerant impact is going to be from our fan coil unit. So we have the centralized plant with a chiller that has the least amount of leakage and the least amount of total refrigerant weight. So that is the most effective from a refrigerant perspective. And then PTEC kind of lands in the middle in terms of refrigerant impact, but is the worst performer in terms of energy efficiency. So it ends up being, looking at the whole picture, the worst possible system that we can design and specify for a multifamily building. So this doesn't necessarily say VRF is evil, because it does result in the best annual performance. But what it does tell us is we need to take a careful consideration of the impact refrigerant has on the building. And that's why we're going to talk about what is in store in the future. So I haven't seen this much in the US yet, but we've got a couple innovative systems that use a different refrigerant type. So this is the Sanco hot water heat pump, and it uses CO2 as the refrigerant. So if you remember, CO2 as a refrigerant has a global warming impact of 1, and traditionally speaking, our 410A has a global warming impact of about 2,000. So it's a significant reduction in refrigerant in the hot water system. You may have had someone present on Sanco already, I would imagine. I'm not 100% sure. Another cool system that's being developed from Mitsubishi is called the hybrid VRF. So if you remember back in the typical VRF design schematic, you have refrigerant going from the outdoor unit to the indoor unit. Well, with this hybrid approach, it kind of splits the difference. So refrigerant is only running from outdoor unit to this branch controller. And then from here, it transitions to a hydronic system. So it takes the refrigerant and creates hot or cold water and then sends that to the indoor units. So not only does it cut down on the total amount of refrigerant in the building, but it's also utilizing this R32 refrigerant, which if I go back, let's see, where's R32? R32 has an impact of 675. So it significantly reduces the impact of refrigerant, not only from a sheer quantity, but also from a impact per pound as well. So this is really neat. I think we're going to start to see this happen more in the US. I'm hoping in the near future. You're muted.
I'm muted. A couple questions came in, and we've got a few people who, you know, a lot of people coming from sort of the single family background. Do you, I mean, typically what we say is, you know, from a single standpoint, you just take a single family home and it becomes a box and then it's multifamily, but usually its energy use and carbon use is higher when you expand all the things that have to go into a single family home to serve one unit. So I guess, can you just speak to us briefly on that, on sort of the difference on what your study was revolving around and how single family might factor in?
Yeah, that's a great question. I don't have the stats in front of me about how a single family home would compare to this analysis, but like you were inferring, when you have a single family home, you have all these services that only apply to one dwelling unit. So you lose a lot of the efficiency if you had a centralized approach serving many dwelling units. So you lose out on a lot of the capabilities here, but you also have less complicated systems in a single family home. So inherently per square foot, you're going to have more impact on a single family home than you would on a multifamily home. But then on the flip side, you have just more density. So you have a lot more stuff happening. So I didn't really answer the question well, but what I'm trying to get to is, you know, if you break it down to per person, you're going to be a bit more efficient if you're in a multifamily approach.
Yeah. And just so you all know, there was a really cool study out of Canada on embodied carbon in single family homes that I think is pretty relevant to us. So it's actually embedded within one of our requirements in Green Star. So I posted a link to that if anyone wants to follow that, and they can find the study in there. Moving on from that question, and actually there was just several questions about multifamily and single family. So I think, you know, I think just your answer pretty much answered all of them here, and the limitations on what you did, and that's where we're at. So, you know, and this question came up, and it was on my mind too, on how, you know, some multifamily projects we're seeing use like mini split systems or using ducted air source heat pump systems. Where would they kind of fit in your mind on that chart a little bit, or can you even make that inference?
Yeah, that's a great question. Let me go back to this this system. So, you know, a mini split, whether it's ducted or not, operates a lot like a VRF system where you have an indoor unit that has a refrigerant line going to the outdoor unit. So it's not going to be the best in terms of carbon performance if you're considering the refrigerant on top of it. That said, there aren't a lot of other great options for residential. I think if you want to be the most forward thinking and reduce the amount of carbon emissions you have associated to your HVAC system, you're likely looking at more of a hydronic system, like a radiant heat system, and even possibly a geothermal system. So you're exchanging energy with the ground with what, you know, like a water loop, a water source geothermal heat pump. Then you don't have a lot of refrigerant going around your home. You might just have refrigerant contained to your ground source heat pump. And it's more expensive. It might not pay off as well as a air-cooled mini split would, but if you're really trying to think about the whole picture, you want to be thinking about how much refrigerant you have in your house and what impact that's having on the total emissions.
So it's really about, yeah, just the piping and the extensions of it. So basically, you know, when you get those multi-head mini split systems, you've got refrigerant all over. But if you've got a single ducted air source system, kind of like an air conditioning, but in this case, you're really then reducing the amount of lines and leakage. Is that kind of what you're thinking of?
Yeah, that's what I'm saying. And also a nice thing about those ductless units is you're saving carbon emissions by not doing duct work. So you just
Right.
have less sheet metal, which has could have a
Trade-off.
big impact.
Yeah.
And without ducts, you don't lose efficiency through ducts. So you've got a better operating performance if you're just supplying air into space without ductwork. So I'm quite fond of the ductless mini splits, and I think it's a balancing act between, again, operational performance and embodied carbon, and that's why we're looking into all this stuff, trying to figure out how you do this and what makes the most sense.
Yeah, and so another question as we're kind of thinking through before we move on, what about, this, they bring up natural gas leakage, and I think what they're saying is perhaps comparing it to a natural gas system, which then is encouraging leakage throughout the entire, from start to finish, right? And so they're saying, the LCA kilogram CO2 equivalent is higher with NGS systems, usually, even if they use less site energy. And so I wasn't sure if that was factored into your conversation. You're just looking at all electric systems.
Yeah, that's a great question. For the purpose of this analysis, we were looking at all electric systems because it would just simplify. Well, actually, I'm sorry. I'm going to step that back. Some of these systems that have centralized, like the fan coil unit where you have to make hot water and chilled water, does have a natural gas system. So that was taken into account. But I think what the person is saying, the infrastructure leakage doesn't get accounted very well in the stat that natural gas has from a source emissions perspective. I think, don't quote me, but I think it's understated. And our perspective is anything we could do to promote and switch over to all electric is going to be the best case for everyone. Maybe not on day one, but as the grid cleans with things like energy policies and things like that, you're going to have less carbon emissions faster if we can get to all electric sooner.
Yeah, good points. And I know typically in like energy models, I don't know what you see, but if you compare gas straight to heat pumps, even air source ones, usually 30-50% energy reduction just straight out in the model, in the energy model, the operations, right? So
yeah, I mean that's also an interesting point because there's a bit of a disservice done in the way we do energy modeling, and I don't know if this came from LEED or it came from ASHRAE, but we've always talked about energy savings in terms of energy cost. And that becomes problematic as we look at these electrified systems because the cost of electricity is a bit more than the cost of gas. So if we have an energy model that looks at energy savings by cost and energy savings by actual energy, like BTUs, we've got significantly more BTU savings, but significantly less cost savings because the cost of utility is slightly more. And I think that starts to skew the conversation. I think we need to be talking more about actual reduction of energy on top of that cost perspective.
Yeah. Thanks.
All right. About 15 minutes left. I'm going to go a little bit quicker. So we talked about MEP. I want to talk about envelope too. It could range from 10 to 25% of the total embodied carbon of the project. This is why, and I'm going to say that this probably isn't super relevant to single family homes, but you can extrapolate either way. Our window systems are inherently more carbon intensive than our solid wall systems. And this is why there's a lot of glass and aluminum, and those are inherently higher carbon emitting materials. This is a curtain wall product, but again, it's per square footage. So a window system, including glass, aluminum, spacers, all that stuff, typically has a range of like 15 to 18 kg CO2 equivalent per square foot. Our solid wall systems, which includes your cladding, your insulation, your stud framing, all that stuff, coming in at about half of that on a typical assembly that I see, at least in Chicago, on low, mid, high-rise buildings, whether it's precast concrete, an insulated metal panel, or a brick veneer, coming in at like 7 to 8 kg CO2 E per square foot. Insulated metal panel starts to get pretty close to these window assemblies because it's got a lot of foam. And as Brett mentioned in the early parts of the conversation, foam is inherently more carbon intensive. Could we do better than 7 to 8 kg CO2 per square foot? Definitely. We can look at more, instead of a brick cladding, we could look at something more bio-based, like a wood piece of wood, wood rain screen or something like that. And that's going to shave this down even more to like the 4 to 5 range. So enclosure matters. It could have a big impact. And what we did is we looked at what we called the ASHRAE prototype high rise for this study. So it's a 10-story building, 85,000 square feet. And we wanted to look at the impact two things have on embodied carbon and total carbon emissions. We wanted to look at the window type. Is it a double pane or is it a triple pane window? And we wanted to look at window to wall ratio. What's the percentage of glass to solid wall, and what happens as that raises or lowers on the building across the whole thing, every surface. All the other assumptions in this building analysis were what we would refer to as code prescriptive for this building typology, just to kind of set the stage there. So this is what we saw, and I'll try and set the, explain this a little bit better. This is similar to the refrigerant graph where we've got a total whole building analysis. So this is the amount of carbon here in kilograms per CO2e, or I'm sorry, kilogram CO2e. And then we have, again, this is on a 60-year life cycle. So what happens across 60 years? And what we saw was as you increase the window to wall ratio, so you add more glass and reduce solid wall, pretty obvious because windows are inherently more carbon intensive, you're going to have more carbon emissions in your project. So I would say typical in Chicago, if you look at a high rise, it's like a 60% window to wall ratio. That's a lot of glass, and it has significantly more total carbon emissions associated to it. What's interesting to look at here is this yellow or mustard graph is the total carbon emissions for this building if it was a double pane window. And in blue here, it's total carbon emissions related if it was a triple pane window. And before we ran the study, I thought on the low end here, so if you didn't have a lot of glass and you went with a triple pane window, you would be in the negative here. It wouldn't be a good idea. You should have just went with a double pane window because inherently there's more carbon associated with triple. But what we saw was even on the lowest end of window to wall ratio with 10%, which isn't a lot of glass, there was still a 1% savings across the entire life of the building because of that extra energy performance you get from a triple pane window. It reduces the amount of space, heating and cooling you need in the space. And as you increase the amount of windows you have in the building, that performance grows and grows and grows. So when we get up to 60%, like our typical Chicago high rise, if you went with a triple pane window, you could reduce the total carbon emissions of the building by 4% or just above 4% here, which is quite substantial from our perspective. And to show you what, what a triple paned 55% window to wall ratio building looks like if it was double paned, that's down here. So 40% is the code prescriptive value. And anytime you go above 40%, you have to take a penalty and you have to trade it off with higher efficient systems. So just wanted to show you, you could do a 40% window to wall ratio building with a double paned, or you could do a 55% with a triple pane. Developers like to see that sort of thing. Gonna summarize the findings quickly here, and then I'm just about wrapped up, so we can jump to questions in a minute here. So I wanted to showcase the kind of the three common scenarios that I see in the industry. We've got a high performance scenario, which typically is a 20% window to wall ratio. That's what I would consider high performance, and I like to see on passive house buildings and other high performing buildings. We've got the code here, which I said is 40%. And then we have business as usual. What we see on our high rise is 60%. So in our 20% scenario, if we went with a triple pane window, we would save just over 1.5% of total carbon emissions. As we move up to 40%, we've increased the total carbon emissions of the project by 5% because we have more glass. The total carbon emissions of the building is going to increase. But the savings you get from switching to triple pane could be up to 3% here. And then again, going up to 60%, another 5% increase to the total. But if you go with a triple pane, you're coming in just above 4% savings. And from my perspective, anytime you get above 1-2%, I think it's a substantial savings, and it should be considered by the owner, developer, whoever's building the building. So key takeaways, refrigerant can result in a large impact to your overall carbon emissions. We can't ignore refrigerant. This is a critical piece of the puzzle as we gain more knowledge about the impact refrigerant has. MEP equipment contributes to the use stage. So that annual use stage that I had mentioned, it's stage B. We do have to think about replacement of MEP equipment across the life cycle of the building and consider that. This was, again, not what I was thinking, but triple pane windows always provided a net positive impact to the total life cycle carbon emissions of the building. Every situation, it was always a benefit. And number 4, more data is needed. We don't have as many environmental product declarations or EPDs from the marketplace. An EPD is something the manufacturer would produce that says, my product has this environmental impact. And we use those EPDs to generate these analyses, and we can't have results without more EPDs. And my final thoughts, life cycle assessment is at the core of efficient and high performance design. Just like energy modeling, we also need to be looking at carbon modeling on all of our buildings if we can. Can't have a low carbon building without an LCA analysis. And as more renewable energy comes online, embodied carbon will be the key issue to tackle. So take away that operational carbon emissions, and we really need to take a look at embodied and the material decisions that we're making from day one. Whew, we did it. We got there. All right. Hopefully I didn't go too fast. I could stay for about 10 more minutes of questions, and then yeah, feel free to email me here if you have any follow-up questions. I'm always happy to discuss this and talk about it. And I do want to give a special shout out to Jess Siska, Anna Morton, and Matt Coleman for helping me do the analyses on these studies for my company.
Hey, great. Thanks, Scott. And we're getting some celebratory claps and stuff. So I think it's going really well. And yeah, we do have some time for questions. Thanks for sticking around a little bit over to help answer if we go a little bit longer. And before we get to those questions, just real quick, as a reminder, yes, this video is being recorded and you can rewatch it, reshare it. And really exciting, we actually started a new embodied energy playlist, and I will be excited to indoctrinate Scott here. And at the top of that list, I think this is a really great introductory session compared to some of the deeper dives we've done in the past. But if you want to take those deeper dives into some of those things, like when we had Stacy from EC3 on, and the Passive House folks out of Europe talking about a tool they have, and all sorts of other things, you can take a look. I just pasted it in the link, and you can get a direct link to our embodied carbon series, and just keep going with that. So, and again, real quick, for those of you watching this session on demand, so not right now, and I just noticed I'm like sharing this screen twice, so where am I? For those of you watching this on demand, make sure to take that 80% quiz with a passing rate or of 80%, and you'll get your CEUs there. And then also for those of you watching this now, mark safe certs at gutenbergcerts.com. Mark that as safe. Check your spam if you don't see it in the next couple of days, and you'll have your certificate. And as always, a huge thanks to our board of directors, our volunteers, our executive director, Jose Reina, and our top tier sponsors, Mitsubishi, Rheem, Build Equinox, CRV, and April Air, and everyone who allows us, all of our members, 233, who allow us to do the work that we do. So Scott, I was intrigued by that window one, and I was going to jump in, and then I realized you were trying to wrap up because I was trying to figure out if you were talking about operations or embodied, but I think you were talking about both there. And I was a little bit jealous because I feel like us here in the residential world, we kind of don't get any of the nice tools until they go through the commercial process, right? We're always last to get all the nice stuff. And so I only know of like some decent tools that are starting to monitor embodied energy, just let alone embodied energy. Recently learned about Passive House in Europe, who has a sort of add-on tool that can look at, when you're running through and doing your energy analysis, you can now look at embodied carbon. But just really haven't seen anything that kind of looks at both when you're doing an evaluation or even one accurately. So what are you using out there, and when do others get access to it?
That's a great question. I think, we're still early days, so it's going to be difficult to do this. And I think it's going to take some time for it to trickle down to single family home users. We're using something called One-Click LCA right now, which is a European tool. And it's essentially a number crunching tool. It's a glorified spreadsheet that we put all the information into. We make selections about what those materials are, and then we get some of the results. And we have to interpret them and make adjustments, account for end of life, things like that. But there's other integrated tools. So if you're working in Revit, or you're a designer, an architect, whatever, something called Tally is from Kieran Timberlake. They're hotshot architects. They developed an integrated tool for BIM. There's other tools being developed every day to help us do this, but it's going to take a little more time for it to be more user friendly. I think right now it's too complicated. It kind of needs to be your full-time job in order to do it accurately.
And is it fair to say that, one of the fears is, of course, just this tool overload, right? You're spending all this time on energy modeling, and in your case, you're probably doing it for 90.1. And we see that for multifamily. And then you got to go and redo it all for embodied carbon, and then you got to merge the two. And so do you see it where you're probably putting in the same inputs to get out both? Kind of like I said, I was really inspired by that window because I could really then see this is where you make those decisions. So
yeah, no, we had to stitch it all together.
Oh, okay.
I had an energy model, I had a predictive energy model on one side. I had the life cycle, I had the embodied carbon model on the other side, and then we pull it all together into a whole building model on the following side. So it's all stitched, it all goes together, but one informs the other and the other informs the other, and it's all interconnected. And you need to be, the whole point is we need to be looking at it all. Otherwise you could get caught up in it. You could think triple pane windows, an extra layer of glass. It's got to be inherently more carbon intensive. Does it make sense to put it on my house if I'm trying to reduce the total carbon emissions of it? And we found that, yes, it is more upfront carbon, but you save more over time by reducing your operational energy use because it's a higher performing window. It's got a higher R value. It reduces the amount of heat loss through that surface. So it ended up being a net gain on every possible scenario, which shocked me.
Where did orientation and shading, and I'm going to add to this question a little bit, area orientation and shading come into your evaluations and considering perhaps additional savings there, and then seeing maybe a value in bumping up the window to wall ratio? Did that play in at all?
That's a good question. That's something I would definitely like to add on to this assessment in the future, because we didn't look at what happens if you add shading, and it's going to be a similar thought process, right? You're adding shading elements that have embodied carbon, and is it enough to offset, the solar gain and cut down on your cooling load? I'm going to say it's probably going to be a net positive too, but I don't have that in the analysis yet, but that's something I'd like to do. I'd also like to take this on the road and simulate other climate zones as well. Is triple pane still going to have that net benefit down on warmer climates like in Texas, Atlanta, Georgia, et cetera? are you still going to see that net benefit, or do you really only see it in colder climates where you have a bigger delta in the winter where it's really cold outside and you're trying to maintain a 70-degree internal temperature? Orientation was split evenly across every facade. So each facade had 40% window to wall ratio, or 50 or 60 or whatever it was.
There's some really good questions here that we're not going to be able to get to, but I just wanted to sort of reiterate. I mean, some of the questions are talking about comparing, if you had a choice to refurbish an existing versus new, and where Embodied comes in. And then other questions kind of getting really into the details about certain site or certain exterior insulation types or insulation strategies, and which one is, which one's better, and then considering up. And then just overall, I think a great thought too about payback, because in the single family and even in the multifamily world, right, you got to get that payback to justify higher performance. And you can see it, especially as our bills are shooting up. But, we just don't see payback when it comes to embodied energy, other than, you had mentioned, reducing materials in general. Do you think that is the opportunity? And what point do you then hit safety issues where you've reduced materials so much that your building just falls down, or an earthquake? I mean, I know it's kind of silly, but those are questions we get. So
no, those are all great questions. I think it's a pretty easy use case to say, if I have less wall surface area, I'm going to have less embodied carbon, and it's going to be cheaper to build because I'm not building as much surface area. That's a simple answer. I would never compromise, the structural integrity of something just to save carbon. I will rely on my structural consulting friends to design a system that meets all the requirements. I'm trying to think of some of the other questions you asked, because now they're escaping me.
Well, those were I was just saying we won't get to those, because
no.
What I wanted to say is, we need calculators to answer all these questions, right? And
yeah, sorry, I remember more now. So carbon payback is really hard right now, but I think it might not get to residential single family for a long time. But as we see things like Local Law 97 in New York, that is going to penalize commercial buildings for having too big of a operating carbon footprint. They're going to have to pay $268, I think, per ton of CO2e above a certain threshold. And we're going to see that type of policy make its way to other cities in the United States. And unfortunately, unless you have a very green, environmentally thinking client, it's going to take these sort of penalties, carbon taxes, et cetera, for you to get a return on investment from improving your carbon performance. So until that happens, we're mostly talking about operational, which is an easy sell, higher efficient system, less money per month to operate it. Makes a lot of sense.
I mean, I almost look at it like building code. I mean, without the building code for energy, we would be building some pretty poor buildings in many cases, right? So I assume then in this case, you're just adding another layer where you're looking at the materials from an embodied energy standpoint.
Yep.
And measuring those, right?
Yeah, and there's some other great stuff happening, again, at more of the municipal level, but things called like a buy clean policy, which doesn't require you to do a carbon calculation, but it does say if you're buying concrete, it has to have at least this carbon footprint. You cannot have a higher performing carbon footprint than that. So it starts to tackle the bottom line, right? If we know concrete and steel and all these big building materials are the biggest impactors in the building, if we set a pretty achievable threshold to hit, then you're doing good work without having to do all the analyses, because it just makes sense.
Right. Sure enough, a prescriptive almost approach to embodied carbon. So Scott, I know you got to get going. I really appreciate you, your time and educating us on this in the conversation. And thanks so much. Just again, remind everyone where they can contact you if they want to reach out or learn more.
Yeah, through my information in the chat. I think it's probably back about 10 chats or so, but yeah, didn't get to your question. Please feel free to email me. I'm happy to have a conversation about any of this stuff. This is what I love to do. I'm so passionate about it. So I'm happy to talk about it at any time. And thanks for having me. And I hope you learned at least like a little little something here. So
I know I did.
until
So,
next time. Yeah.
all right.
All righty.
Thanks. Yeah. Thanks so much, Scott
Take care.
Farbman,
All right.
dbHMS. Take care, everyone. Have a great rest of your week. Stay cool. Bye.
See ya. Bye.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.